In this video, we're going to be looking at a question that asks to identify a conic section from a given equation by means. So we're going to be looking into answering this question by means of the method of diagonalization of a matrix. The example we're going to look at is the following. Consider the equation 16x squared plus 24xy plus 9y squared minus 3x plus 4y equals 0. Geometrically, what this equation represents is a set of all points on a Cartesian plane, all points xy, for which the equation holds. And so if I start plotting all these points, I'm going to get a certain curve. Maybe I'm going to get something like this. And then I want to know which kind of curve this is. And because of the nature of the equation, where I've got a x and y squared as being the highest power, and so basically what I have here is a polynomial of two variables. Because of that feature, we're going to get one of the conic sections as the graph. What is a conic section? So you might already know that, but just to remind you, if you take an infinite cone and you cut that cone with a plane, the trace that it's going to leave on the plane is called a conic section. And the possible traces that it can leave are straight lines or parabola or hyperbola, depending on at which angle does the plane cut the cone. For example, if I cut it at this angle, then the trace is going to leave the intersecting line between the cone and the plane is going to be of this shape, which is going to be I think it's called an ellipse, right? So that's one of the conic sections. If I bend the plane a bit further, then eventually this end is the ellipse is gonna grow, and eventually it will never end. So I will have a never-ending ellipse. And so this is how I can get other shapes like hyperbola and parabola. And I can also get straight lines if I cut it vertically. If I just already this picture I put here is a cut of the cone and the paper, well, the blackboard on which I'm putting the picture, right? So you can see we get two straight lines as a result. Okay, so one way of approaching to solve this problem is to rewrite this equation in a matrix form, and namely, we want to give it the following shape. We want to present it as the row vector xy multiplied by a certain matrix. We're going to figure out what this matrix is, and then multiplied by the column vector xy. Then this part will take care of this part of the equation, this part. So that will correspond to this part over here, and we still need to have something corresponding to what we've got here. And we can do that by adding another term there, which will be the column xy multiplied by a certain row, and equate all of that to 0. And of course, the row we're going to use here, it's quite evident from what is written there, will be minus 3, 4. But what about the matrix here? Now, the whole point of this method, in order for it to work, what we want is to have a symmetric matrix here. Imagine I had some values A11, A12, and if it's a symmetric matrix, then here I'll have the same A12 and then A22. If I expanded this out, what would I get? Let's multiply first the middle one with the right hand side one. So that will be A11x, sorry, that should be a matrix. That will be A11x plus A12y, and here down here I'm going to get A12x plus A22y. Right? Now we multiply this further on the left hand side, and then I'm going to have x times A11x plus A12y. So we're multiplying here a row with a column, right? Plus y times A12x plus A22y. And if I open up the brackets there, I'm going to have A11x squared plus 2A12xy plus A22y squared. You see? Sorry that is not visible, but now you see. Okay, what I want to do next is to compare this expression with that one. And by such comparison, I notice that A11 must be 16 and A12 must be 12, so that 2 times A12 gives 24, whereas A22 must be 9. So once I figured out this once, later I can just remember the method used to figure it out. And the method is that the coefficient you put in here and in here in the diagonal entries of that matrix, of that symmetric matrix, will be the coefficients of the x squared and y squared respectively. So that's 16 and 9. Whereas the coefficients you put in here will be half of the coefficient of the xy term. So that's going to be 12 and 12. That's the symmetric matrix that allows presentation of this equation in two variables x and y in the matrix form. Okay, so let's get rid of some of the extra things here. We don't want this anymore. So that was just a little bit of a theory here, telling us how we can figure out the entries of the matrix. But now let's continue with discussing the method. So the first step in the method is to rewrite the equation in the matrix form. Now the second step of the method is to make a certain change of variables. So let's denote by capital X the column vector xy. And let's introduce a change of variables, by which we mean we want to substitute into this equation x equals some matrix P times x prime. The x prime is not the derivative of x. X prime consists of new variables x prime, y prime, which are not derivatives of x and y at all, which are some expressions of the x and the y. Okay? And the way I can get x prime and y prime out of the x and y is to multiply both of these sides of this equality with the inverse of the matrix P. So we do want P to be invertible matrix. Moreover, we will want P to be orthogonal matrix. And remember that orthogonal matrix is a special type of an invertible matrix. It's the one whose columns are orthonormal. So if x is equal to P x prime, by multiplying both sides by the inverse of P, but being orthogonal means that the inverse is given by the transposition, right? We get that the transpose of P multiplied by x is equal to x prime. So the new variables x prime and y prime and the old variables x and y are related with each other through these equalities, through the equality x equals px prime and transpose p x equals x prime. Okay. What we want to do next is to substitute these into the equation. Now, before I do that, let me also show you a little bit of, not show, but at least mention a little bit of geometry of of this substitution. So what we're basically doing here is we are trying to get the equation represented in a different coordinate system with respect to which the equation will have more recognizable form, so we can see that, for instance, if it was this shape, it would be a parabola. And the matrix P is going to have that effect of changing the coordinate system and taking the vector x in the old coordinate system to figure out what is the corresponding values for the same vector in the new coordinate system. We figure that out by multiplying this x by the transpose of P. And then it turns out that this P will be exactly made out of columns which are the vectors in the new coordinate system, the one that makes the equation have a more familiar form. So this is what we're going to head towards. But before we get there, we need to do a few steps. So what we want to do as a next step in the method is to substitute, as I said, substitute the vector x being equal to px prime. So I want to put that into the equation. So I can see that because x is that vector, I will get the transpose of x, and I need the transpose of x, right? Why do I need the transpose of x? Well, I have transpose of x right here. The x is the column vector, but here I've got a row vector, so I need the transpose of x. Because x is equal to px prime, the transpose of x will be the transpose of px prime, right? But now the way transposition works with matrix multiplication is that it swaps around the order of multiplication and transposes each matrix. So we'll have here x prime transposed multiplied by p transpose, okay? So then let's take these and substitute into the equation. Namely, we're going to substitute in here that, because that's x transpose, and in here we're going to substitute that. Moreover, also in here we're going to substitute that. Okay, great. So let's do the substitution and let's see what we're going to get. So, but at the moment we are not saying what the matrix P is. I'm going to first do the substitution, and then I'm going to make a comment about the nature of the matrix P. At the moment it's an arbitrary matrix which we're trying out in the substitution to see if we can maybe simplify things. Okay, so keeping in mind that the matrix all the matrix P does, it changes the coordinate system. By a substitution like this, we're not damaging the shape of the curve. So when I get a new equation now in terms of x prime and y prime, if that new equation gives me a parabola, then the old equation also gave me a parabola. It's just that the parabola it gave me wasn't located in a nice way according to the original coordinate system, but with respect to the new coordinate system, it now aligned in such a way that I can recognize from the equation its parabola. Okay, so that's the idea. Great. So let's do the substitution, and then we'll get the following. X transpose equals x prime transpose p transpose is going to give me exactly that. So we have this term here in the place of the vector xy here. Then I have still the same matrix 16, 12, 12, 9. And then the column vector, the x column vector, is of course p x prime. And then I have plus minus 3 times 4 multiplied by p x prime, right? And that is equal to 0. Okay, now what I'm aiming at here is to find, is to select the matrix P in such a way that this thing here will be a diagonal matrix. Now the reason why I want this to be a diagonal matrix is so that because when it's a diagonal matrix, these entries here will be 0. And remember where these entries come from. These entries are half of the coefficient of the xy entry. And so by choosing the P matrix in such a way that this is a diagonal matrix, I'm going to get here an expression where the xy term is going to vanish. There will be no xy term because it will be multiplied by 0. Okay? So how do I do that? How do I get this to be a diagonal matrix? Well, that's exactly solving the diagonalization problem, right? The orthogonal diagonalization problem. Note this matrix is symmetric, and so finding a matrix P so that this thing is equal to a diagonal matrix is exactly solving the orthogonal diagonalization problem for the matrix A that's given here, for the symmetric matrix that's given here. All right, so now our task is to do that. Our task is to find the eigenvalues and eigenvectors, because that's how we can find the orthogonal diagonalization of a matrix, right? So let's do that. To find the maybe we give a little heading here, eigenvalues of the matrix A equal to 16, 12, 12, 9. We need to solve the characteristic equation, which is the determinant of 16 minus lambda, 12, 12, 9 minus lambda. The determinant of that equated to 0. And that's going to give us 16 minus lambda multiplied by 9 minus lambda minus 12 squared equals 0, right? Okay. What do we do here? Do we just multiply this out? We'll get lambda squared. Here we have minus 9 lambda minus 16 lambda, so it's minus 25 lambda. And then we have minus 12 squared. So the characteristic equation is all of that equals to 0. Okay, so let's solve the characteristic equation. Oh dear, how do I solve this equation? Well, we could solve it by using the usual method for the formula for quadratic equation, but if we are a bit smart right here, we could see, and I wasn't smart right there, I paused the video and thought about it, and then I actually cheated because it's like 10:30 now, so I didn't want to extend too much into the night recording the videos. And then I thought to myself, oh dear, look at this. When I said I cheated, I meant I found the answer first on the internet with a calculator. And then I thought, wait a second, look at this. This is so easy. This is 4 squared. 9 is 3 squared. And 12 squared is 4 times 3 times 4 times 3. So you see it's 4 squared times 3 squared. So 12 squared is equal to 16 times 9, right? Okay, anyhow, with much embarrassment in how I got this answer, but satisfied by the nice explanation I showed you here with the orange color, we get that this expression is equal to lambda minus 16 times lambda minus, plus, just a moment, sorry. Where are we now? One of them should be a plus, right? But which one? Something is not adding up here. No. Wait a moment. What I told you here is quite a bit of nonsense, because we are not having here a plus, we have a minus, right? So the fact that that times that is equal to 12 squared doesn't help us at all, because here we had 16 and 9 both with a plus sign. So that means that this is all rubbish. So you see, I can't even, I'm so bad at calculating things, I can't even calculate it right with a calculator. I'm getting a bit worried now that we are going to get some nasty numbers here, but maybe it's worthwhile for us to check that all our calculations were right. So is the matrix that we got there right? Let's see. Yes, that does look right. 16, 9, 12, and 12. That part is right. What about the characteristic equation? 16 minus lambda, 9 minus lambda, and then we have there. Oh yes, of course. Look at this. I was quite silly about that. Of course, this is not right. And instead what we get here is something much nicer. Lambda squared minus 25 lambda. Exactly, because 16 times 9 is equal to 12 squared. We're going to have here plus 12 squared. Well, let's write it properly. Plus 16 times 9 and minus 12 squared. And so this falls away. Maybe I should use a different color here. It's not like there's a mistake there. And then we get lambda times lambda minus 25 equals 0. And so the eigenvalues that we get here are 0 and 25. Wonderful. We found the eigenvalues. Now we want to find the eigenvectors, right? So to do that, we will have to put the extended matrix in the form 16 minus lambda, which is 0. So we'll have 16 minus 0 there, 12, 12, and 9 minus 0, and then 0, 0. And let's see what this extended matrix gives us. Oh, sorry, you can't see that. There we go. We'll then get 16, 12, 12, 9, 0, 0 by, well, this is equal to that, but then by row operations we can reduce this to 4, 3, 0. And down here we're going to have, if we divide by 4, we're going to have 3, no, by 3, sorry. 4, 3, 0 as well. So the top one we divided, the top row we divided by 4, and the bottom row we divided by 3. And then it ends up being, so with one more row operation, we eliminate one of the rows, and this is exactly what should happen, otherwise there will be no eigenvector, and it's not impossible since the eigenvalue is there. Sorry again for not seeing what I was writing. So now from this we can see that we would pick out 1 in the second entry and 0, no, not 0, sorry. So we'll have then, if I put a value for k2 to be 1, then here I'll get that, we'll get the value of 3 over 4, right? So that will be eigenvector for lambda equals 0. And for lambda equals, so let's write this down. And for lambda equals 25, to get the eigenvector, we have to subtract 25 now instead of the 0. So here we'll have minus 9, 12, 0. And then we have 12, and we have minus 16, right? 0, and that's equal to dividing both the top one by 3. We have minus 3, 4, 0, and well, this is actually a row operation, so I shouldn't write equality here. I should rather put an arrow. Then in the bottom one, dividing this, we're expecting to get something that's a multiple of the other one row, right? Because we want to get zeros here. So dividing this by 4, we're going to get 3 minus 4, 0, and indeed it is a multiple, so we can eliminate the second row, and then from this we can extract the eigenvector 1, and now we're going to have, just a moment, was I right with 3 over 4 there? I needed to move this on the other side, so it would have been minus 3 over 4, sorry about that, because the 3 would go on the other side with a minus sign, right? And so here the signs are the same, and it's not 3 over 4, but then it's 4 over 3, right? So these are the eigenvectors for that eigenvalue. I mean, these are the eigenvectors for those eigenvalues. Okay, with orthogonal diagonalization, which is what we're trying to get, we're trying to get a matrix P that's orthogonal matrix. We want the eigenvectors to form an orthonormal sequence, and so because they corresponded to different eigenvalues, 0 and 25, they automatically will be orthogonal to each other. But now we also want them to have length 1, so we have to rescale these. By the way, just a remark here, we could have as well selected something nicer looking, something like minus 3, 4. Just multiply both by 4, and also here we could have selected instead 4, 3. That looks nicer than 4 over 3 and 1. Okay, but we have to rescale these still, so let's do that. So let's keep track of the eigenvalue. So for eigenvalue lambda equals to 0, we had minus 3, 4, and we want to rescale that. We have to multiply this by the reciprocal of its length, and so the length will be 3 squared plus 4 squared, that's 9 plus 16, which is 25, and square root of that is 5. So the length of this vector is 5, so we want to rescale it by scaling down by 5. So we'll have minus 3 over 5 and 4 over 5. And if we're not sure about this, whether it's a unit vector or not, we can double check this by finding its norm. This term squared plus that term squared and square root of that, and that's indeed going to give us 1. Okay, in a similar way we rescale the other one. The entries in the other one are just different from this one by a sign, so the length of the other vector is the same, and so then we can use the same scaling factor. So for 3 will be rescaled to 4 over 5, 3 over 5, and then these are the eigenvectors we would want to use in the matrix P. So now we can design the diagonal matrix D, which will be 0, 25, and the matrix P will be minus 3 over 5, 4 over 5, and 4 over 5, 3 over 5. Remember that the order in which the columns of P should appear should correspond to the order in which the eigenvalues appear in the diagonal entries. So that this eigenvector here corresponds to the 0 eigenvalue there, not down there, but here, and this eigenvector here corresponds to that eigenvalue there. Okay. Now we go all the way back and take this answer back there. To be more precise, we'll see where we stopped there and put this answer in. So this is what we had here. In our calculation, that's where we were, right? And we want to bring this calculation down back here, and now we know what should the P be and what should the D be. And we want to put it back into the equation and then expand the equation out. So that's the next step in the method. And keep in mind that x prime is the column vector of x prime, y prime, which are not derivatives, but different variables. and the relationship between x prime and x, the previous variables, which we now don't care anymore, but there is a certain relationship via the matrix P, which we've written above. Okay, so we're going to write here the transpose of x prime, so that will be x prime y prime. And then what we've got here is the diagonal matrix, which is 0, 0, 0, 25. And then we've got the x prime matrix, the column, x prime column. And then we have plus, and now we have to do some computation here. We have to take this matrix P and multiply x prime with that. And then further multiply this by minus 3, 4. Okay. So let's carry out that calculation to see what term are we going to end up with here. I'm just trying to find space for it, so I'm going to copy this matrix P down here. So at this moment we're trying to fill the space here, right here. Plus something equals 0. So once we get the answer, we're going to take it back and put it into the place of the question mark. So that's the matrix P, and as you see from here, it should be multiplied on the left by this row, and on the right by the x prime column. And so let's carry out the calculation. Perhaps it is easier if we take out as a common factor 1 over 5, right? So we have 1 over 5 times something. Okay, so what is it times by? Minus 3, 4 times minus 3, 4, 4, 3, and then times x prime, y prime. Something tells me I should first multiply the two matrices by these two matrices, maybe because the symmetry of the reoccurrence of the numbers there tells me that. Let's see if that's going to give a simpler way of computing this. So 1 over 5. Now let's multiply these two matrices here. So that's well, it's a column matrix multiplied by a square matrix, and so we're expecting here. Sorry, it's a row matrix multiplied by a square matrix. So we're expecting here to get again a row matrix, right? So the first entries here is going to be minus 3 times minus 3, which is 9, plus 4 times 4, which is 16. So 9 times plus 16 is 25. And then we have minus 3 times 4, and then 4 times 3, and they together give 0, right? So this is then multiplied by, so maybe I was not far from truth. It did give us something simple. And so we can now bring in 1 over 5 in there to be clever and eliminate that 25. Although, of course, the rest is quite straightforward. So this is going to give us 5 times x prime. Look how simpler it is. Originally we had, if I go back all the way here, I had minus 3x, 4y, and look at this, just 5x prime. This is so neat, right? So what we have to put in here in the place of the question mark is then that we need to put here 5x prime. And now we take the next step, which is the following. So what we want to do now is to multiply this out. Remember, we started off with an equation in terms of x and y, which we couldn't recognize what curve does this describe. So we put it in the matrix form, and then we did some change of variables, and now we want to bring it back into an expanded equation that's not in the matrix form, so we can recognize the shape of the curve by looking at the equation. And if you remember, the way it worked is that these coefficients here, they were coefficients for these ones here, they were coefficients for the x squared term and the y squared term, whereas these ones here gave the half of the xy term, but now they're 0. So in fact what we have here is going to be only the y prime term, right? And remember, y prime is not the derivative of y. It's just another symbol for a variable. In this specific video that we're talking about now, you usually in calculus y prime is the derivative of y, but not now. Okay, so this is going to give us 25 times y prime squared. That's the answer to that part there, plus 5x prime equals 0. We know now what shape this is, what curve this is, right? Divide out by 5, we get 5y prime squared plus, you see how simpler this is compared to what we had originally. This is so elegant, isn't it? So what is this? I can express x prime in terms of y, right? It's going to be minus 5y prime squared. It's a parabola. It's a parabola, but if I want to actually plot the parabola, how would I go about it? Okay, so here is, right, so first of all, let's say that we've answered the original goal, which was to determine which kind of conic section we were dealing with, and the answer to that is that it's a parabola. Now, the next question, which we might be curious about, is how can we plot it on the plane? So can we actually use the calculations we did here to get a plot for this parabola? Okay, so, and this is where we're going to apply the idea of change of coordinate system. So with the old coordinate system, in the old coordinate system, the matrix P there. Okay, so let's go back here. Namely, let's go back right here. Remember when we did this x equals p x prime. So this change of variables, what does it actually do, right? If I had put here a column vector 1, 0, this would be picking out the first column of P, right? So, but what is column vector 1, 0? Remember, x prime is in the new coordinate system. The coordinates, the vector given in the new coordinate system as a pair of numbers. So in the new coordinate system, what would have coordinates 1, 0? Well, in the new coordinate system, that would be the coordinates of the unit vector on the x-axis, right? In the old coordinate system, that's the value on the left-hand side. So this x gives the value of the old coordinates, the coordinates of the vector in the old coordinate system. So this, let's make a note of that. So this is old here, old coordinate system, and this is the new coordinate system. So something that in the new coordinate system has coordinates 1, 0, in other words, the unit vector on the x-axis of the new coordinate system, to check what will the coordinates of that vector be in the old coordinate system, we just have to multiply that by p, and we multiply a column vector with 1, 0 by p, we'll select out the first column of p. So the first column of p, not of this matrix, but of p, is going to be the old coordinates of the new unit vector on the x-axis. And the same way, the second column of p is going to be the coordinates of the unit vector on the y-axis, the new y-axis, the coordinates of those in the old coordinate system. So in other words, what we're saying here is that these eigenvectors that we put inside the P, these things, they are the unit vectors on the axis of the new coordinate system. Isn't that wonderful? So we can now plot them, right? So they are vectors, the unit vectors in the new coordinate system, but they are given here in terms of the old coordinates. So in the old coordinate system, we have to plot these vectors now with these coordinates, right? So it's going to be minus 3 over 5, 4 over 5, and so where is that going to lie? The x coordinate being, maybe we can be a little bit precise here and marks the over 5s there. So let's say this is 1 over 5, 2 over 5, 3 over 5, 4 over 5, 5 over 5, 6 over 5, 7 over 5, 8 over 5, and so on. And then we do something similar here. And something similar here. And the same here. Okay, so now let's find the vector whose coordinates are minus 3 over 5, 4 over 5. So the x coordinate is minus 3 over 5, so we have to count 3 steps backwards here on the x-axis. And so let's make a mark there. And the y coordinate is 4 over 5, so we have to go 4 steps on the y-axis, 1, 2, 3, 4. Okay? And so that's going to be the x prime axis, right? The unit vector on the x-axis of the new coordinate system. Okay, so what about the y prime axis? Well, that's given by the second column of P, and so that's 4 over 5, 3 over 5. And so the x is equal to 4 over 5 and the y equals equal to 3 over 5. So 1, 2, 3, 4, and then 1, 2, 3. So it's, okay, maybe it's here and it's there, and together they give us this. And it's not surprised that these two things should be orthogonal to each other, right? And moreover, they will also have length 1. So this is the y prime axis. And the direction here is also important, of course. Okay. Now, in this new coordinate system that we've just drawn, the red one, and let's actually extend this into proper axes. In this new coordinate system, the equation of that conic section is given by this formula. What does that mean? This is a parabolic equation, right? So I can actually like rotate my head a little bit to the left, and so I can think of this as the y-axis. This is the x-axis, and this tells me y equals minus 5x squared, right? So the parabola is going downwards against the direction of the x prime axis because of the minus sign there. It's stretched by a factor 5, and it is a parabola. Okay, so a rough picture for this would be just to draw in a parabola here. Let's use the blue color for that. That goes out like this. If I want a more accurate picture, I would have to figure out where does the parabola cross the axis. But now these are the old axes, right? And so to figure that out, I would have to put some zeros in here. So let's say x equals 0. If x equals 0, to get the y-intercept, we're gonna have 4y squared plus 4y equals 0. And okay, so let's actually compute this. So when x is equal to 0, we will have 9y squared plus 4y equals 0. And so we can factor y out. We'll have y times 9y, sorry, plus 4 equals 0. And so y is going to be minus 9 over 4 over 9. Okay? So that's roughly minus 2 over 5. Because I've got those markers there. I've got those markers here, so it should be roughly minus 2 over 5. And so each one is 1 over 5, so my picture is actually not very accurate. It should rather cross here. And then symmetrically, the other side will be, of course, symmetric because it's a parabola. So something along those lines. Something like that. Sorry, let me try this again. Whoopsie. There we go. Something like that. It should be this symmetric according to the x prime axis. So something along like that. Okay. Great. So we've now been able also not just to identify the conic section, but also to plot it by first plotting the new coordinate axis and then plotting the graph relative to the new axis. But now the plot, of course, if we erase the new axis, then will be in terms of the old axis. And so you see, in terms of the new axis, the equation is so simple. It's just the usual parabolic form. But in the case of the old axis, it looks very complicated the way it's arranged with respect to the old axis, and then no wonder that we had such a complicated equation right here. Okay, so let's just summarize the whole story. So in the summary, I'm going to maybe identify certain steps and number them. So we are given an equation of a certain conic section. We want to know what conic section it is. So that's the step number 0 when we are given the initial information. Okay. Then the first step is to rewrite it in a matrix form. And so we identify this matrix here that comes up from there. The coefficients there obtained in a certain way. 16 and 9 are coefficients of x squared, y squared, and 12 are half of the coefficient of the xy term. Then also this one is written out in the matrix form. Then we need to propose change of variables. So this is the key formula there. That's how we're going to propose the change of variables. So we can think of this as step number 2. But of course, it includes this step here where we have representation of x as a column vector. So this is step number 2. These are the formulas we're going to be using for substitution. The discussion here was just the theory discussion that kind of was aiming us to get an orthogonal matrix there. So once you get practice of applying this method, you don't have to go into these steps anymore. And then the next step is to do the substitution, to substitute this number 2 into number 0. And so that's how you get something called number 3. And the step after that is to find, so at this point the P is not a specific matrix, you're just using a symbol P there, but now you want to find a P that would make this whole product to be a diagonal matrix, and that means solving the diagonalization problem, the orthogonal diagonalization problem in fact, and of course that's the same, that reduces to solving eigenvalue problem and then fixing up the eigenvectors you get at the end. So the eigenvalues that you'll have to find, and to find those eigenvalues, well, I guess the next step is to identify the matrix you're working with, so that's number 4, and then you start searching for the eigenvalues. So the next step is then to get the characteristic equation here, number 5, and once you have the characteristic equation, you have the eigenvalues, and then for each eigenvalue, maybe I should call this step 6 to get the eigenvalues, and then for each eigenvalue you get eigenvectors. Step 7, there are 2 of them. There will always be 2 because we're dealing here with 2 by 2 matrices. So that's step 7 and step 8 to get the 2 eigenvalues. And then is what we know what to do then is to put them back into what we want is to normalize them. So they turn out to be orthogonal to each other because they correspond to different eigenvalues, but if the eigenvalues are the same, we might have to fix them up to make it orthogonal. And once we do that, then we normalize each eigenvector. So step 9 and 10, so for each one of them. And then after making sure that lengths are 1, so by normalizing I mean making lengths 1, then what we do in step 11 is to write down the corresponding diagonal matrix and the matrix P. And the way it's going to be used is to substitute into this equation we had earlier, with the P transpose that matrix A and P being now equal to the diagonal matrix. And then we also have to compute on this side here what to do. So the substitution is going to give us step 12, the result of the substitution, and then we multiply things out. But to multiply things out, remember we had to figure out this coefficient here, so that's part of the substitution process. So I'm not going to include it as a separate step. And then once we have step 12, we multiply this out and we're going to simplify the equation, so that's going to be step 13. And then in step 14, step 14, we recognize what curve it is, and in step 15, if we also want to do that, we give the plot of the curve by first plotting the new coordinate axis, and that's done by making use of those eigenvectors we found, those normalized eigenvectors we found, and then with respect to that new coordinate system, plotting the curve, the conic section, according to the new equation we got for it in step 14. Alright, so that is the method for identifying a conic section by making use of solving the diagonalization problem. And that you can consider this as one of the applications of the diagonalization problem. And you can see here, you can kind of get a flavor here to the extent of simplicity that sometimes diagonalization of a matrix can bring in, namely that originally we had such a complicated equation, and then after diagonalizing the matrix, after finding the right coordinate system and rewriting the equation for that coordinate system, we discovered that the equation is much, much simpler. And so that's the purpose of this example of this method, to give you an application of diagonalizing a matrix.